Let me welcome you to this lecture. We have now learned the chemistry of metal alkyl complexes, and we have seen that these ligands, that is the alkyl ligand, uses a sp3 hybridized orbital to bind with metal centers, and that is how it acts as a one electron donor. That is, if you take say a methyl ligand, then one of the sp3 hybridized orbital of the methyl group, three of the sp3 hybridized orbitals are going to bind with hydrogens here, while one of the sp3 hybridized orbital containing one electron from carbon is now going to act as a sigma donor. So it forms sigma bond with metal orbitals, and that is how the alkyl group essentially acts as a one electron donor and forms a sigma only metal to carbon bond. Now we have a few other ligands which form similarly, which uses hybridized orbitals to form metal carbon bonds, and these ligands or the chemistry of these ligands we will discuss during this particular class. That is the olefin uses one of the sp2 hybridized orbital to bind with metal, or an aryl ligand again using a sp2 hybridized orbital containing one electron may also bind with metals, and similarly an sp hybridized orbital on alkynes may also bind to metals in a similar fashion. So all of these ligands, they can form sigma bond with metals by using a hybridized orbital, unoccupied hybridized orbital. So that is, well, in this case, in these two cases, we see that an sp2 hybridized orbital binds with metal center, while in case of the alkyne, we see that an sp hybridized orbital binds with metal center, or binds with overlaps with metal orbitals. So these ligands form complexes in this particular fashion. So we know the ligands, or we term these ligands as this one, as because it is derived from an alkene, this is known as alkynyl ligand, while this is phenyl ligand, while in this case we call this this is not alkynyl, this is called alkenyl because we derive it from alkenes, while this is derived from alkyne, so we call it alkynyl ligands. And since these ligands form sigma bonds with metal center, and that is why we call the complexes formed by these ligands and again as metal sigma alkynyl complexes, metal sigma phenyl complexes, or as aryl complexes, and these are called a metal sigma alkynyl complexes. Specifically because we have to distinguish these complexes from other complexes. Again, these ligands can form complexes by using their pi electron density or using the pi bonding orbital to bind with metal centers, and they are different type of complexes compared to the ones that we see over here, because in those cases a pi bonding molecular orbital is used to bind with metal centers, and then we call the complexes formed by the, say, alkene. In this case, if it binds to metal center in this way by using the pi electron cloud, then we call these complexes as metal olefin. Similarly, the aromatic compounds can bind to metal centers by again using the pi electron cloud in this particular fashion. Then we call them metallocenes or aryl complexes. While alkynes can also bind to metal centers by using their pi electron cloud, and in this case we call the complexes as metal alkyne complexes. So just to distinguish between these two types of binding, or to specifically mention that, because in these cases, in these three cases, the ligand forms sigma bond with the metal center, and by using one of the hybridized orbital, and that is why we mention specifically that these are metal sigma alkenyl complexes or metal sigma phenyl complexes and metal sigma alkynyl complexes. These type of complexes where or sigma alkenyl complexes are also known as sigma vinyl complexes, as this is a vinyl group we see, and these are also called as metal acetylide complexes, because this particular group we identify it as acetylide group, and at times we also call this sort of complexes formed by the alkynyl ligand as metal acetylide or metal sigma acetylide complexes. So we'll discuss the chemistry of these metal alkynyl complexes, metal phenyl complexes and metal alkynyl complexes here, and we will discuss the chemistry of these metal olefin complexes or metal aryl complexes or metal alkyne complexes in a later lecture. So here we will discuss the chemistry of alkynyl, aryl and alkynyl complexes, actually all sigma type of ligands. But if you look carefully, these ligands also have pi star orbital. Apart from pi bonding orbital, they also have pi antibonding orbitals. All of these ligands, here also we have the pi antibonding molecular orbital, as well as in this case we have 2 pi antibonding orbitals along with the pi bonding orbitals which are filled. So apart from the sigma bonding interaction, which is formed by the filled sp2 hybridized orbital in this case and a filled sp hybridized orbital in this case, the pi star molecular orbital can, there is a possibility that metals can donate electrons to these pi star molecular orbitals present in this ligand. So these ligands are somewhat intermediate between only sigma donor ligands like alkynes, where there is no empty orbital to accept pi electron density, and on the other extreme we have the pi donor and a sigma donor and pi acceptor type of ligands like carbon monoxide or phosphines, which can accept pi electron density from metal centers, or nitrosyl or dinitrogen ligand, which we have already discussed. These ligands also have these alkynyl, aryl, as well as alkynyl ligands also have empty orbitals to which electron density from metal can be can be transferred, or they can also form pi backbone or uh, by donation from metal to ligand can occur in these complexes as well. Now, if it happens, if we assume that pi back donation from metal to these ligands or the pi star molecular orbital of these ligands happen, then we will observe that the metal to carbon bond distance in these complexes should be shorter than the sum of the covalent radii of the constituent atoms, that is the metal center and the carbon atom in respective hybridization. And also what should happen is that the carbon-carbon bond distance in these cases, in all of the cases, should increase because we populate the pi star molecular orbital in all of these molecules. If we transfer electron from the metal to the pi star molecular orbital, then the bond order between the carbon atoms should decrease, and that is why there should be a lengthening of carbon-carbon bond distance. So this should happen if there is any pi back donation or if the pi back donation occurs. So let us look at some of the experimental data and verify if such pi back donation occur in these sort of complexes where olefins or aryls or alkynes uses a hybridized atomic orbital to form sigma bond with metals. So let's look at some structural data. So this is an alkyl complex of platinum. Square planar platinum complex. So this is an alkyl ligand. And if we look at the platinum to carbon bond distance in this particular compound, we will find it to be equal to 208 ppm. Picometer, sorry, and the covalent radius of platinum is equal to 131 picometer, while the covalent radius of carbon in sp3 hybridized state is equal to 77 picometer. So if you look at now another platinum complex containing an olefin ligand now, or alkynyl ligand in this case. As you see that one of the hydrogen is missing, so the carbon atom is using one of the sp2 hybridized orbital to bind with platinum in this case. While you keep rest of the complex identical to the previous complex over here, where there is only platinum to carbon single bond is present because this is an alkyl ligand, while in this case we use an alkynyl ligand where there is a possibility of metal to carbon back donation or metal to and therefore the bond distance in this case should be shorter, and what you find that in this case the bond distance, platinum to carbon bond distance, is equal to 203 picometer, while the covalent radius of platinum remains same. In case of sp2 hybridized carbon, the covalent radius is equal to 67 picometer. And then if you look at now another complex of same type, but only you substitute the alkynyl ligand with an alkynyl ligand in this case, now the platinum to carbon bond distance becomes 198 picometer in case of this particular compound. 131 picometer is the covalent radius of platinum, while for carbon in sp hybridized state the covalent radius is equal to 60 picometer. Now if you sum up these covalent radius of the constituent atoms, that is platinum and carbon, in different hybridized state, what you will find in this case, the sum of single bond distance that we get by adding up the covalent radius for platinum and carbon is going to be equal to 208 in this case, and in this case it is going to be 198 picometer, while in this case it is 191 picometer. So if we compare the bond distance that is observed for the platinum carbon bond to the sum of the covalent radius of the platinum atom and the carbon atom in the respective hybridized state, what we see is that there is not much difference between the covalent radius, between the sum of the covalent radius that we get with the observed bond distances in all of the cases. So what does it indicate, or the bond distances that we see in these cases do not indicate the presence of any considerable pi backgradation from the metal to carbon in this alkynyl ligand as well as in this sigma alkynyl ligand. So though there is there are empty orbital are present in these two ligands, and the metal has the ability to donate electrons to these empty orbitals in the ligand, we do not see any considerable backgradation happening in these cases. Also, if you look at the carbon-carbon bond distances in these two compounds and then compare the carbon-carbon bond distance with, say, that you see in case of the pristine ligands, that is in case of ethene as well as in case of alkyne, you will observe that there is not much difference in the carbon-carbon bond distance, that is in case of the free ligand with the coordinated ligand here, and that also again signifies that there is the electron density in the pi star molecular orbital has not increased in these complexes, and therefore there is less possibility of metal to ligand pi back donation in these complexes. Now, many of these complexes, that is alkynyl complexes, aryl complexes, as well as alkynyl complexes, can be prepared by the following synthetic strategy that we use for preparation of metal alkyls, and some of the strategies which we did not discuss in the preparation of metal alkyls we will discuss here. So metal alkynyl complexes can be prepared by oxidative addition of HX to metal olefin complexes or alkyne complexes. That is, if we take now take it to be R, and then if we now add HX, that is either HCl, HBr or HI, then oxidative addition of HX will take place on this platinum atom, and what will happen is we will end up with this sort of a product. That is, a metal alkynyl complex is formed in this way, and if you observe here, the hydrogen atom here is ceased to be metal center, and it happens because first during the oxidative addition process, hydrogen gets attached to the platinum center, and then thereafter it migrates to this carbon center to form an olefin, and this is how this metal to carbon bonds actually forms, and this is happening because now oxidative addition takes place and the hydrogen atom gets attached to the platinum center initially before it migrates to the olefin carbon atom over here. So then There is another way through which you can prepare metal alkynyl complexes, that is by nucleophilic addition of on cationic metal alkyne complexes. So if you take metal alkyne complexes, say if you count the number of electrons in this molecule again, what you will find 8 electrons from iron, 2 electrons from carbon monoxide, 2 electrons from phosphine, and this alkyne ligand which uses now the pi bonding molecular orbital to bind to its metal center. This is not alkynyl complex, this is a metal alkyne complex, and this is again a 2 electron donor, and since there is a positive charge, positive charge on the complex ion, we deduct 1 electron, and we also have to add the electrons of this CP ligand, and then what we get 10 plus 4 14 plus 5 19 minus 1 18 electrons. So this is an 18 valence electron, and now nucleophilic addition on this compound can take place. That is, you can use a copper alkyl phenyl reagent here, which acts as a phenyl. We will source of phenyl group, this reagent is, and then now this will go and attack on one of the olefinic, on one of the alkyne carbon atom over here, and what we will obtain CH3 here, and in this case we observe that the phenyl group is now trans to the metal center over here, or we end up with a trans product here, because the nucleophile attacks the alkyne group over here from the side which is opposite to the side through which it is binding to the metal center, and that is why we end up with a trans product here in this case, unlike what we saw the formation of the cis product in case of the oxidative addition to the metal center by this HX group. So in case of these metal alkynyl complexes, alkynyl complexes, the double bond here, because it uses only a sp2 hybridized orbital to form a sigma bond with the metal center, and double bond or the pi bonding molecular orbitals are intact here, and these can again now be used to bind with metal centers here, so that these alkynyl ligand essentially can act as a sigma pi bridging ligand in this way. So we'll see one example where this sigma alkynyl ligand acts as a sigma pi bridging ligand by using both the sp2 hybridized orbital as well as pi bonding molecular orbital to bind with metal centers. So if you take Fe2CO9 and then do reaction with trans dibromoethene, So this is how the alkynyl ligand here we see acts now as a sigma pi because it forms sigma bond with this particular iron center, while it uses the pi uh, uh, pi bonding molecular orbital to form another bond with the other iron center over here, and it bridges the two iron centers by using this sort of sigma pi bridging binding mode. So then we will now look at metal aryl complexes. These are again, as we have discussed, the metal aryl, one of the sp2 hybridized group of the aryl ligand forms a sigma bond with the metal center, and again this acts as a one electron donor ligand, and the one of the best way to prepare these metal aryl complexes is to use aryl magnesium halide or aryl lithium reagents to react with different metal salts. That is how we also prepare the metal alkyl complexes. So one can prepare, say, you can take titanium tetrachloride and you can take phenyl lithium, or you can also take phenyl magnesium, say, bromide here, and then do reaction. This will give you essentially tetraaryl phenyl titanium will be formed, where these phenyl groups forms essentially sigma bond with the titanium center. Now the stability of these compounds are no more stable than these metal alkyl complexes. We have already discussed about the unstability or different decomposition pathway of these metal alkyl complexes, and these metal aryl complexes are also similarly, they also undergo decomposition and are not stable or as stable as these metal alkyl complexes. But some of these complexes, we observe that these acetyl to metal PR3 2. So these are square planar complexes of nickel, palladium, and platinum metals. So these complexes are unusually stable as compared to other metal aryl complexes, and the reason for the stability of these complexes, if you look at carefully, so these are square planar complexes. So the two phosphine ligands, say, and the two acetyl groups we can draw in this way. Now, if you look carefully, the these aromatic rings will lie on a plane which is perpendicular to this plane of the board here. And because of this steric effect of these substituents on the phosphines, the acetyl rings now cannot rotate freely through the along this, or this, this particular bond, carbon metal bond cannot rotate freely because because of the steric effect of this steric hindrance that is there because of these substituents on the 2 and 6 position of the acetyl group with the substituents on the phosphorus atom. So it gets locked in this particular position. So the acetyl group always lies on a plane which is perpendicular to the plane of the board here, and this essentially so these are the pi star say these are the pi star. These are orbitals from the pi star molecular orbital of the mesitide ligand over here, while this is the dxy atomic orbital of the metal center, which is filled here in case of this one. So we assume this to be the x direction and this to be the y direction, and if the direction which is perpendicular to the plane of the board, if we assume it to be the z direction, then this is the xy orbital over here, and this orbital is filled in case of nickel, palladium, and platinum. We can square planar complexes, and now there can be metal to pi star. This backdonation can happen, or metal to ligand backdonation can happen efficiently in this case because the ligand is locked in a position which allows efficient overlap of these filled metal dxy orbital with pi star molecular orbital in the mesitide ligand, and that is how it essentially this particular metal carbon bonds here are more stronger as compared to metal carbon bonds in conventional or other metal aryl complexes or phenyl complexes. So because there is pi backdonation in this particular compound. Also, if you see now these substituents over here, the substituent on the phosphine ligand as well as the substituent on the mesitide ligand also block the attack of any other ligand that can on the metal center that can happen along the z direction. So they offer steric hindrance for any attack on the metal center by other ligands, and that also stabilizes or makes the complex kinetically more inert. Also, what you can notice is that because of the substituent on the phenyl rings over here, the hydrogen atom and the beta carbon, there is no hydrogen atom on the beta carbon atom in these ligands, and therefore beta hydride elimination in these complexes is also can be neglected. So this is how, that is the reason why such mesitide complexes of these D10 metal ions are they can be isolated easily, and they are more stable as compared to other metal aryl complexes. So we'll now discuss about these alkynyl ligand. If you look at this alkynyl ligand or this acetylide group, this is isoelectronic with cyanide or carbon monoxide or dinitrogen, and that is why the complexes formed by this acetylide group or this sigma alkynyl ligand, their properties, that is their stoichiometry as well as the color and magnetic properties, they are quite similar to the cyanometals or metal cyanide compounds. And in fact, this acetylide ligand is a one electron donor, and it is considered to be a pseudo halide, and the complexes formed by these acetylide ligand are essentially, they are part of a classical coordination chemistry as compared to, and they are not regarded really as a metal organometallic complexes because they are considered to be pseudo halides. But if you look at the basicity of these ligands, then what you will observe that the acetylide ligand is much more basic as compared to, say, cyanide, carbon monoxide, or dinitrogen, and it is why these complexes, acetylide complexes, though they are considered to be classical coordination complexes, they tend to undergo hydrolysis very easily, and that is why one needs to prepare them by using anhydrous solvents like ammonia. And the preparation methods is also similar to the preparation of, say, cyano complexes. So if you can start with, say, cyano complexes, and then do reaction with, say, sodium acetylate here, and then you can replace the cyanide ligands and prepare acetylide complex or alkynyl sigma alkynyl complexes by this particular way. So here you see that instead of 6 cyano groups, here we have 6 acetylide group. So we can name this compound as potassium. This is ethynyl hexaethynyl chromate 3 in this way. So that is how we can name these complexes by following the IUPAC guideline. So these complexes, as we have said, they undergo hydrolysis very rapidly because this acetylide ligand essentially is highly basic in nature, and also they are quite explosive in nature. These compounds, and their thermal stability increases or decreases in this particular order. That is, aryl substituted acetylides are thermally more stable, while the acetylide itself are less stable as compared to the aryl substituted alkynyl ligands, while alkyl substituted acetylide complexes formed by these alkyl substituted acetylide ligands are least thermally stable, and they are quite explosive in nature. So one can increase the hydrolytic stability of these alkynyl ligands is quite high in case of the complexes, acetylide complexes formed by these group 11 metal complexes, that is copper 1 and silver 1 and gold 1. The reason is, if you take, say, copper acetylide complex, then the acetylide group uses the pi bonding molecular orbitals to bind with copper acetylide, the copper atom from another a nearby this copper acetylide molecule here in this particular fashion, and that is how now the copper is now, you can see that the coordination number of the copper atom has increased now to 3, and the acetylide ligand uses, are essentially bridging these metal centers in these complexes, and that is the reason why these copper, silver, gold acetylide complexes are hydrolytically more stable as compared to other acetylide complexes, because now there is more interaction or intermolecular interactions that are essentially, the copper atoms or the metal centers, the coordination number is higher and they are more stable, or they are less prone to be attacked by water molecule here, and that is why they are hydrolytically more stable. So this essentially brings us to the end of this lecture. What we have learned during this lecture are 3 different types of ligands, or 3 different types of sigma bonding ligands. These are alkynyl ligand, aryl ligand, as well as alkynyl ligand. We have seen the difference between the ligands when they use the pi bonding molecular orbitals to bind with metal centers. We name the ligands in a different way, and their chemistry is also different. While in case of these alkynyl, and aryl complexes, we see that they use one of the hybridized orbital and to bind with metal centers, and we also looked at the synthesis of these alkynyl, aryl, as well as alkynyl complexes, and we also discussed the stability of these complexes. That is, in case of aryl complexes, we have seen that one can stabilize these complexes by playing with the stereochemistry, and this by playing with the stereochemistry as well as the steric effects. And we have also seen that in case of alkynyl complexes, the stability can be increased if by increasing the coordination number of the metal center. So with this, let me conclude this lecture. I thank you very much for being with me during this lecture.